Hi everybody, welcome to our next topic in grade 12U physics. So today we're going to be talking about another form of potential energy, elastic potential energy. And I want to give you a bit of a spoiler alert. If you haven't finished your lab yet, you might want to pause this video or close it and come watch it again another time, because I kind of might spoil the ending to your lab. With that said, before we can talk about this idea of elastic potential energy, we have to talk about springs. And specifically, we want to talk today about what happens to the forces on springs. So as I'm pulling a spring or pushing a spring, what sort of forces are involved? And what's going to govern this is something called Hooke's law. So named after a guy, again, a contemporary of Newton. Um, and he actually played with springs a lot and came up with this expression called Hooke's law. And it has to do with, again, stretching a spring. So let's start with a couple terms here. So the first one, we're going to call a spring when there is no forces acting on it. And whatever length that is, we're going to call it the equilibrium length. So in this diagram here, it's diagram A. And so we're going to call this length the equilibrium length, or you might also see it as x naught. So the length of this spring right now is x naught, or it's in equilibrium. And then if I apply a force, it's going to extend the spring, and we're going to call this distance x. And we're going to call the force exerted by the spring on the hand as Fx. So something to keep in mind a little bit, that if the hand is applying a force in the spring to the right, Newton's third law says the spring is going to apply the exact same force on the hand, but to the left. So our terminology, again, we're going to say an extension is a positive x value, and a compression would be a negative x value. And so we get these sort of two expressions for Hooke's law, but again, they're both the same, just whether we're talking about to a spring or by a spring. So as I mentioned, a bit of a spoiler alert here, that hopefully in your experiments, when you graphed the force applied to your spring versus its length, you would have got a linear relationship. Your graph wouldn't have looked exactly like mine. Your graph probably would have started somewhere over here and gone up somewhere like this. And I'm going to imagine that is, and I'm hoping that is, because I didn't have you graph the extension of this spring. What I actually had you graph was just the whole length of this spring. So again, I'll leave to you what that intercept means, because it's one of the questions on the lab, but I think hopefully it's pretty obvious now. But if we do this, lo and behold, we get a straight line. And again, straight lines in science are fantastic. They mean we found some sort of relationship that's important. And so this guy, Hooke, got a law named after him because of it. So it's a pretty simple law. Remember, the general equation of a straight line is y equals mx plus b. And since this goes through the origin, we can write it as just y, or in this case fx, equals some constant times x, which is our x coordinate, or axes here. And so we're going to call, in this case, the slope k, which means there's k right there. So this is the force applied to a spring to stretch it. And then conversely, a force applied by a string would just be the same with a negative sign in here, because we'd actually have the inverse force, so our slope would be going down. And we're going to call this k a spring constant. And this again tells you how stiff a spring is. So it's going to be different for each spring, but notice from dimensional analysis, you should get this constant is measured in newtons per meter. So for instance, if I have a spring constant of 10 newtons per meter, that means every meter I want to stretch this spring, I need to pull it with 10 newtons of force. Or if I want to pull it 2 meters, I'd have to apply 20 newtons. So again, hopefully, again, you can see that a bigger spring constant means kind of a stiffer spring. And this nice pattern holds quite well for almost all springs, as long as we don't go too large or too short. If we go past a certain distance, we get this area called deformation, where the spring just kind of stretches and is destroyed. But most of the cases we're going to deal with in this class are ideal springs. And funnily enough, an ideal spring is only one that obeys Hooke's law. So pretty much if it's a linear relationship, it's an ideal spring. And the reason it's going to do this is because we can assume it experiences no friction. So it's not rubbing on the table. Neighboring atoms inside of the spring aren't really affecting each other. So it's friction-free both internally and externally. So here's our idea again for the force on a spring. So again, hope I haven't ruined your lab experience, but hopefully you got something kind of similar. All right, on to the next part then. So let's do a quick example of this. So we have a spring. We're using it to hang a mass from it. And I've told you its initial length. So before I hang this mass on it, it's 12.2 centimeters. So in the terminology I just showed you on the first page there, this would be our x naught. And so x naught is 12.2 centimeters. That means the equilibrium length. But then I hang this mass on it, 2.5 kilograms, and it stretches. It stretches, so now it's 20.1 centimeters long. I want to know a couple things. The first one being the spring constant. So again, that spring constant is that letter K. So I really want to know what is the K, what is the spring constant, and the only relationship we have right now that involves K is the extension and the force and the extension. So hopefully we have those. And let's kind of go back and see what we do have. So if I'm letting this apple hang freely, let me just quickly draw a free body diagram for this apple then, or a mass or whatever you want to have here. So I have, there's the apple. I'm going to have two forces acting on it. Of course, I'm going to have gravity pulling down, but I'm also going to have this spring pulling up. So gravity, force, gravity, and I'm also going to have the force of the spring, which we're calling Fx. And again, if it's hanging freely, hopefully you can see that the sum of the forces should be 0 because the mass is not accelerating. So that means the force of the spring in this case is just equal to the gravity force, which again, hopefully this is not a surprise, but that's just given by mg. And so that's an easy number to figure out because we have the mass, there it is right there, and g, of course, we're assuming we're on Earth. For the extension, again, that you might think at first glance it's 20.1 centimeters, but it's not, because remember this value is the extension of the spring. So how much it's stretched. So it's 20.1 take away 12.2. So I'm getting 7.9 centimeters. But of course, we need to consider or concern ourselves with units. And we want to have a spring constant in SI units, which means this should be in meters. So 0.079 meters. All right, and a relationship between these three values, again, is our Hooke's law expression. Fx equals kx. I'm hoping you can do this, but I'm getting a k when I plug in my numbers of 310 newtons per meter. So again, what that means is every meter I want to stretch this spring, I have to apply a force of 310 newtons. So the next question, how long would the spring be if the mass were decreased to 1.8 kilograms? So instead of hanging our 2.5 kilograms, I'm going to hang 1.8 kilograms. I hope you can see that it will be somewhat shorter than 20.1 centimeters because, again, it's not as big of a mass. So with that sort of ballpark in mind, let's go back and do a calculation here. So it's the same spring, so we know it has the same spring constants, 310 newtons per meter. And just like before, if we're letting this thing hang freely, we know these forces are balanced. So the extension force, the spring force, is just given by the gravity force here, which is mg. And we're looking for x. So again, I'm going to jump to the end here and spoil the party. My calculator spits out 0.0569. And of course, we need to pause and ask ourselves what this means. So notice again, I used SI units. You can follow it through, and I'm going to get meters. And so it looks like maybe their spring is 5.69 centimeters long. Something doesn't seem to add up just because our spring initially was 12.2 centimeters. So shouldn't it be somewhere down here? And the answer is yes, and hopefully you can figure out why. Again, this value is the extension of the spring, so how much it's changed from its initial value. So that means the length of the spring is that distance added to the equilibrium or x naught length of the spring. So I'm getting 17.9 centimeters. It's this plus this, of course, in centimeters. And the last part, what force would be required to make the spring 10 centimeters long? So let's go through and do this one here. So again, we know the same K. The X in this case, again, we want to make it 10 centimeters long. So again, X is not 10 centimeters though, because X is the change from the equilibrium length, which was 12.2 centimeters. So really my x is negative 2.2 centimeters, and of course put that in meters. And I'm getting an extension spring, or extension force of negative 6.82 newtons. And whoa, we have a negative. What the heck does that mean? Well, what that means is I'm not stretching this spring, I'm compressing it. So instead of hanging this mass here, I'm pushing it up. So this is going to have to go in the negative x direction here. And again, that makes sense. We have to push a force into it to make it compress. So the one thing I haven't mentioned yet explicitly, but I hopefully, again, it follows along, Hooke's law applies equally well for compressions or stretches of the spring. So whether we're having a negative x or a positive x, Hooke's law still holds for these ideal springs. Okay, so there's Hooke's law and the forces on the springs. But of course, the title of today is this elastic potential energy. So we have to figure what that is. So we're going to give it the symbol E with a little e as the subscript. So energy of elastic potential, or elastic potential energy. And so that's, I'm just going to use this of the textbook. Follows along with it. All right, so our definition for elastic potential energy is the energy stored in an object due to it being stretched, compressed, twisted, or bent. So most often we're going to deal with being stretched or compressed. So there's sort of our definition, but we want to then get like an expression for it. So in order to do that for this elastic potential energy, let's consider again the forces that we're applying to a spring to stretch it. So this is kind of the force extension graph that you should be used to from the first page. But the one thing to remember that work, remember, is force times distance. And again, the one thing that I haven't mentioned explicitly, and I maybe should have by now, another way to get this is by looking at a force displacement graph, right? So if we have a constant force applied over some distance, the work is just going to be this area here. Notice it's F times delta D, F times delta D. So we can actually do that for a spring, but unfortunately, this isn't a constant force. This is an increasing force, but it's okay because we've got still a pretty easy shape here. It's a triangle. The base of this triangle is x, the height of this triangle is kx, and so we're going to get an area then of 1/2 x kx, or 1/2 kx squared. But again, since we're doing work to store elastic potential energy, we can say any work done was storing potential energy, and so here's our expression for elastic potential energy. Pretty simple, I think, in terms of the form of the expression. And again, it goes on board with our other sorts of expressions, so we know EK is 1/2 mv squared. We know that the EG, gravitational potential energy near Earth's surface, is just mgh. And for this one, again, the elastic potential energy is 1/2 kx squared. Just to give you a bit of a foreshadowing, the one difference we have between all three types of energy is that the elastic potential energy does not involve mass. So a lot of the problems we solve, the mass won't cancel out like we're used to doing when we do conservation of energy problems. So that's just another wrinkle we'll have to deal with when we get to. All right, so let's jump into some examples here. So here's a spring suspended from the ceiling, so very similar to the one we had in our first example. I told you it's on extended length of 10 centimeters. I told you it has a spring constant of 280 newtons per kilogram. And I told you the mass is added to the spring. And so I want to know a couple things again in this one. The first one, I want to know the length of the new spring. So again, the length of the new spring, once it's hanging freely, we're going to say the forces are balanced. So the spring force is just given by the gravity force. And so again, I'm going to jump to the answer for A, because I think I've done a bunch of these already. I'm getting a new length of the spring of 18.6 centimeters, or written in SI units, 0.186 meters. And again, just to stress, that means this distance is 18.6 centimeters. That's not the extension, that's the total length of the spring. So for B, when we want the energy stored in the spring, I don't want to use 18.6 or 0.816. I want to use the difference between that and the original length. So that would be 0.86 meters, because that's how much this spring has stretched. So I want to find the elastic potential energy stored. It's just given by 1/2 kx squared. I've got K, 280. I've got X right there. The only caution I give you again is watch out. This is squared. Don't forget the square. I'm hoping I didn't do that, but when I calculate this, I'm getting 1.03 joules. So again, we're storing this energy that we can use to do some work. And just to give an example of doing some work, let's look at a similar situation, but now we're using a spring to launch an object in the air. So this kind of is the basics of the spring launchers that we used in class. Remember, we tested our projectile calculations. We saw how awesome you guys were at predicting where these things landed. And so this is sort of the mechanics of what was going on in there. We've got a spring. Its unextended length is 12 or 20.5 centimeters. So here, right here, we apply some force to the ball or to the spring, so it squishes. So the spring is only 15.2 centimeters long, and then we let go, and then, of course the ball goes flying up. And I want to know what is the new height of this ball. What height will it reach? So kind of the maximum height. And so what we're going to do for this method is let's use energy conservation, because again, one of the lovely laws we have is that energy is conserved. So any energy before a situation happens has to be the same as any energy after it's the same situation. So I'm going to be using this kind of compression as my initial. I'll call it 1 here. And I'm going to call the ball at the top of its flight 2. So again, in like grade 11, we just said the potential plus kinetic would be equal to potential plus kinetic. Or summed up a little different, the total energy stays the same. So ET equals ET. And just to differentiate, instead of doing 1s and 2s, since we're going to have a lot of subscripts floating around, I'm going to follow along with your textbook does, and we're going to call this ET equals ET prime. And so prime would just be after the event happened. So again, we now have 3 forms for energy we have to be concerned with: EG, EK, and EE. So all of these before, the sum of them before, have to be equal to the primed versions, or the energies afterwards. But with some careful sort of considerations, we can actually cancel off or zero out a lot of these terms. What I'm going to suggest is let's call this our h equals 0. This will be our baseline for our height. And here's our x naught value, right? So here's our sort of reference levels. And so if we do that, that means I can actually get rid of this initial potential energy. I can get rid of this initial kinetic energy so it's not moving. And the only form I have initially will be elastic potential, because I'm storing some energy in the spring. Conversely, for the primed versions, the spring isn't compressed or stretched anymore, so I can kill off this one. And we want the maximum height, so that means kinetic energy there would be 0. So again, by some careful choices of our reference levels, we've simplified our problem substantially. And we're just saying the elastic potential energy initially is equal to the gravitational potential energy finally. So 1/2 kx squared equals mgh prime. And again, the one concern, our mass doesn't cancel off here. But again, I think it makes sense. If I compress a spring by a known amount, I imagine a heavier ball would not go nearly as high as a lighter ball, because it needs more energy to do so. All right, so again, we have all the values we need. K is given right here. The extension will be the difference between these two values in meters. M we know, right there. G, of course, we know because we're on Earth. And so I'm going to cut to the chase here. And the height I'm getting is 23.9 centimeters. So again, just to drive this home, what this means is this ball will be 23.9 centimeters above this line. So from here to here will be 27 or 23.9 centimeters. If I wanted the height above the bottom of the spring, say it was resting on a table, I'd have to add this 15.2 centimeters. All right, so again, I think that example is done.